we're going to talk about, ultimately, the most important topic here is going to be this one, something called electric potential. But it's one of my kind of my favorite lectures. There's no fancy demos or anything, but I like those things in physics that make me feel smarter than other people. And there is no more widely used topic in physics that has these kind of contrast between how much it's used and how much it's really understood than electric potential. I mean, and we'll see this as we go through. But I'm going to get to something called gravitational potential first. It's important to note, we're going to start by talking about gravitational potential energy. This is something that we treat in Physics 1. We're going to have to relook at a little bit. So we're going to, in an effort to make electric potential energy more understandable, we're going to have to maybe complicate gravitational potential energy just a touch. But it's easier to picture with gravity, so we'll start there. So what we know about gravitational potential energy is U gravitational is mgh. But like a lot of things in physics, when I taught you that last year or whatever, or 2 years ago, I wasn't completely honest with you, or I didn't give you the fullest picture possible. This works, but it works as long as you are on the very close to the surface of a planet. Because you guys understand that G is a factor of, we've looked at G as the gravitational field. Remember, that's capital G, mass of the Earth, divided by the radius of the Earth squared. That would be, now this radius of the Earth squared is your distance away from the center of Earth, right? Well, if you are in an orbiting spaceship, or even on top of Mount Everest, G is a little less for you, because you're a little farther away. And so, we don't really discuss that aspect of this, because we just assume even the tallest skyscraper that we're going to drop objects from, G is still basically 9.8. Right? It's all within 9.8. So, this works, but only as long as you are right next to the surface of some planet. A more complete picture would be this. How much energy you have, well, the units have to work out. So, mgh is going to work out to be joules. So how much energy something has depends on where it is. So if this is, here we'll make it blue. And we'll make some object that we're talking about red out here. My barboard is caving in on me here. What it really is going to depend on is this. A more complete picture of your gravitational potential energy is going to be G, the mass of, in this case, the Earth, the mass of the object, some U, some satellite, doesn't matter, divided by the distance between them squared. Not necessarily the radius of the Earth, right? But that's force, right? Mass. So we're missing something. Well, actually, we have too many R's. So I'm going to get rid of that. And the reason that goes, one of the reasons, or one of the explanations I can give you for why that goes away is, do you agree with me that work also is joules? Right? And work is force times distance, right? So what I had up there when it had a squared was force. If I multiply that by a distance, so in other words, if I took this force would change as distance went away. But if you took the average of it, your force times that distance would give you your energy. Which means when you were done that, gravitational potential energy doesn't have the squared in the bottom. Because you're multiplying by a distance and you would get this. So gravitational potential energy, a more complete way of looking at it is this. Yeah, it's weird when you think about it. I mean, look at that thing. That means the farther away you get from Earth, the less potential energy you have at that point. In a way, right? See, what happens is this. We don't actually have less. The way we describe it is that out here at infinity, so some ridiculously far distance away, you would have no energy because you would be so far away you wouldn't feel force. And therefore you couldn't be dropped onto the Earth, right? So what we say is that that's zero, and the Earth is in something called a gravitational potential well. It is like falling into a well. You would call this zero. As long as you're walking on the ground, you're safe, right? But if you happen to get close enough or fall into that hole, then all of a sudden you would start to consider your energy at this point. So gravitational potential energy, like I said, it gets more complicated. So this is true, but I can still look at it like this right now and make sense of things. So for electricity, by the way, it's this same formula. So for, the electric potential energy from a point charge is going to be, not G, we know this, it's going to be K, Q1, Q2, divided by the distance between them, not squared. We don't use potential energy all that often. It comes up, definitely, and energy is always important. So let me ask you this. What we do use is this concept. You have a shelf. Thinking. Should I bring that up now? Yeah, we'll talk about it. Yeah, okay. So, which location? The top of the shelf or this bottom shelf here? Which location, here's a person, just to give you a frame of reference, which location has more energy? Say the top. Well, we've looked at this little trick question before. What if I put a bowling ball here and a ping pong ball here? Which one has more energy? Which one you want falling on your toe? Remember, energy is all about, can it hurt you? Which one has more energy? This one does, right? See, I can't just describe the location as having energy, because it depends on what I put there. We've caught this depends on what we put there deal, right? With electric field and electric force. I can't say how much force something has until I have two of them, right? But it would be nice if I could describe how much force I could have, right? Because I think we all would agree that comparing apples to apples, in other words, putting apples here and apples here, right? Sorry, for those of you who didn't see on the screencast, apples here and apples here. Or bowling ball here and bowling ball here. Or even ping pong ball and ping pong ball. If we compare the same thing in those locations, which one would have more energy? The top would definitely have more energy. So we need a way of describing that location as having, you ready? Ready? This is having the potential for more potential energy. Take a second, let that sink in. All right? This is more likely, this is going to have more potential energy for the same amount of mass. Now, I don't know for sure. Maybe you put a ping pong ball there and a bowling ball down here, but as a location, this will generally have more potential energy. It ultimately depends on what you put there. How much energy you have, because it takes two to make energy. But this, as just a location, what we would say is this has more gravitational potential. And we do not put the word energy at the end of that. Potential, I think. That's spelling right. We stop after the word potential because we want to say energy because that's what we're used to, but we just stop. Now, we didn't look at this concept in Physics 1. There really wasn't too much of a need to. But gravitational potential, really for us, is just how high something is, right? Because if we keep it simple and we look at gravitational potential energy, that's mgh. Well, what determines it really, that we're talking about the gravitational potential, I believe this is the letter we would use, is just GH. And it really just comes down to H, doesn't it? The higher you are, the more gravitational potential you have. Not energy yet, because I got to find out how much mass you're putting in. Now, we don't talk about this in Physics 1 because, let's face it, we could simply say, which one's higher? And everybody knows, right? The higher one is going to probably produce, could have more energy. But for electricity, this means an awful lot. So, what we would say, by the way, for gravitational potential is a moment ago we said gravitational potential energy could be looked at as big G, mass 1, mass 2 over the distance between the two masses, not squared. Right? That would be energy. What about gravitational potential? What do we take away? We only have one m, and that would be the mass of the Earth, the thing that's pulling it down, right? So it really would be G. I'll even put the Earth there just as a clarifier, and your distance from the Earth. So this is the most stripped down formula we have. If you think of the progression, we started with electric force, and we said K is, although we could do gravity, I guess. We should stick with gravity. Talk about gravitational force, and we said that it was big G, mass 1, mass 2, distance between the objects squared. And then we said, well, what if we didn't know one of the objects? We still want a way to describe the force at a location. So we said, sure, we'll call that the gravitational field. Sorry, I'm all in electricity mode. I guess we'll call that lowercase g. The gravitational field, which is going to be big G, mass 1, divided by the distance between the center of that mass and any location you want to pick. Wherever you want to look at the field strength. And we said gravitational potential energy is going to be big G, mass 1, mass 2, but only R, not R squared. And this thing called gravitational potential is big G, mass R. Right, so it's the most stripped down form that we have. Is energy a vector? Is kinetic energy a vector? Calculations of kinetic energy. Do you recall ever having to use arrows? No. That's a beautiful thing, my friends. These two are vectors, and therefore, that adding and subtracting is not as simple as just adding and subtracting. There's angles and stuff involved. However, these two are scalars, and therefore, adding them is literally adding. The math for doing these is easy as hell. But the concept is different. Now, let's run through this for electricity. What do we know so far about electricity? Well, we know electrical force. And this is all for a single point charge, but G. There I go using G for electrical force. There we go. Get rid of that. There we go. K, Q1, Q2, distance between the two objects squared. The electric field is K, Q1, just one of the charges, divided by the distance between charge and some point that you're interested in, divided by that distance squared. Electric potential energy is going to be K Q1 Q2 divided by distance between them, not squared. And then, my friends, electric potential, the amount of energy you could have depending on how much charge you put in that location. Just like this is the amount of potential energy you could, gravitational potential, depending on how much charge, how much mass you bring. So, electric potential, K, Q1, over the distance from that charge to some location. So, here's a positive point charge. Which location, the green one or the red one, has a higher potential energy, electric potential energy? So be careful. In order to have energy, how many charges do you have to have? You have to have two, right? It's like saying, how much energy is on that shelf, on the top of that shelf? Well, it depends on what you put there, right? You open that closet door, top shelf, and there's just a couple hats and a pair of gloves, and they fall on your head. That wasn't a lot of energy, was it? But that location is still dangerous because you wouldn't put a bowling ball there for that very reason. Because your mind says that has a lot of gravitational potential. It doesn't use that phrase because you've never heard it. But that's what it says. It says, no, put the bowling ball on the floor. Right? That location is inherently, something about it is dangerous, right? Well, from an electrical standpoint, which one of these is more dangerous? Because see, now, because if I ask you about electrical potential energy, you can't answer. It depends on what charge you put here and here. I'm asking about locations. So I should ask, which of these has a higher electric potential? So which one has a higher electric potential? Think of it this way. If I put a positive charge, same positive charge in each of those, which one's going to shoot off faster? Because it's going to repel, right? Green is, isn't it? Right? In fact, think of it this way. In order to pull, I have to work hard to pull this back, right? I got to grab that thing and do work against the electric field. This is important. This is analogous to if you have to lift something off the ground, isn't it? I have to do work against gravity. But that energy's stored, isn't it? On the screencast, I just lifted something up and then let it go. Just so you know. Showing that when you do work against the field's pulled one way, you're pulling against it and moving an object. So moving that green charge, if there was a charge there, moving it, that's gonna make it have even more and more energy, right? So the closer you are in this case, the larger the amount of energy, which is counterintuitive to gravity, right? I mean, gravity is, but in this case, this has more electric potential than this guy. So, here's the thing. Electric potential is the amount of energy per coulomb. Now, if I know the electric potential here is, I'm just going to make something up, 57. I'm not even going to say the units because it'll... Then, if I put 1 coulomb of charge at that location, how much energy will I have? So what's electric potential again? It is the joules per coulomb that you put in a location. So if I put 1 coulomb there, guess what? I'll have 57 joules of energy. If I put 2 coulombs there, I have 57 times 2. Why did I pick 57? 114. Got it. Right. If I put a half a coulomb, I have half, and so forth and so on. This is the number of joules per coulomb that I would have at that location. Straightforward concept, right? We're talking about energy, which is hard enough. Now we're talking about energy per coulomb of charge. So you place something. Everybody agree this is like one of the most esoteric topics that we've talked about? Really? Okay. It's funny. Look up esoteric. It means like, wow, that's pretty far out there. Like, do you know what the units for electric potential are? It's called the volt. Everybody on this planet walks around talking about voltage, right? How many people you think really understand that it's really the energy per coulomb? No, right? No, like us and a few others. Maybe them. They kind of heard this last year, but I'm not betting on it because they're too busy with their memes. But here's the thing. Have you ever heard voltage described as electric potential? Never. Don't you think this is a little odd? You always hear it as voltage. Folks, this should strike you as very odd. If I ask you how far it is from here to the door, we talk about the distance from here to the door, right? There's a word for that. And we measure that distance in meters. And this whole bit I'm going through is just an explanation of it is a tough concept, and it's a tough concept because here's the clue. Nobody uses the actual name of the concept. From here to the door, I would say is a distance of 6 meters. It would be like somebody come up and saying, what's the meterage between me, right? Because the entire concept is described by its unit. They don't say potential difference. What do they say? What's the voltage? That's like saying, all right, how long is it between now and the end of class? What's the minutage? Right? What's the secondage between now and the end of the day? Right? What? No, it's time. Well, we don't use potential difference. We don't use electric potential, which we both. Well, we use the unit name to describe it. I mean, it's the only one. Its letter in a formula is V, right? Its unit is V. Because it is a tricky concept. Now what you want to keep in mind is that the volt is joules per coulomb. Volts are connected to energy. All you need to know in order to find out how much energy. So the simplest way I can give you this is that if you want to know how much electrical energy you have at a location, if you know the electric potential at that location, just multiply by whatever charge you put there. Because voltage is joules per coulomb, and when you multiply by charge, which is coulombs, you get joules. This is true no matter what. No matter how you create the potential difference. If you know the charge you want to put at that location, you can find the energy at that location. So, you know how we describe this shelf, for example. That shelf, let's say that shelf's about, we'll call it about 2 meters high. I know it's not, but we'll call it about 2 meters high. So, what is your joules per kilogram at the top of that shelf? So we're talking about a shelf that is 2 meters high. What would your joules per kilogram be? Your gravitational potential, by the way. Which I don't think they use voltage, I think they kept that letter because really this is a concept, I bet, that originated more in electricity and they realized could be applied to gravity. I could be wrong. But what would it be? Well, it's everything but how much mass you put up there. So we have mgh, correct? Let's just do GH, right? Because I don't know how much mass I'm putting up the top of this shelf. I don't know that. But the characteristic of this is 9.8 g times the 2 meters. So it would have a gravitational potential at that point of 19.6 joules per kilogram. So the top of that shelf will give you 19.6 joules worth of potential energy for every kilogram that I put up there. How much energy does it have? Well, all I got to do is multiply. Tell me how many kilograms you're putting up there. I'll tell you. Multiply. If it's 3 kilograms, I'll multiply by 3. Right? I'm trying to drive home how this formula works. For electricity, if you know this is the value, you're going to know. If they want to know how much, you want to know how much energy you have at that location, they better be telling you there's another charge. All right. Let's see. I guess the only other thing, this isn't everything about it, but the only other thing I do want to point out is this. So let's say you have a collection of point charges. Nah, it doesn't really matter. There we go. And a location. Boom. And let's say those charges are, do this, we'll say Q1, Q2, Q3, and Q4. Now let's say Q1 is 10 coulombs, Q2 is negative 7 coulombs, Q3 is 5 coulombs, and Q4 is negative 1 coulombs. So what would be your net electric potential at that location? Remember I said that the math with these is so much easier? Remember, if we had a point thing, we would have to worry about vectors and all that other crap. Don't worry about that. If you want to find the net potential, each one of these has its own distance. We'll call it R1 away, right? And this one has a distance, call it R2. And this one has a distance R3. And this has a distance R4. And we'll assume we know those distances for a second. I don't even care about it right now, but I did want to put some charges in there with numbers to help you see this. So this is all you have to do, ladies and gentlemen, is do K Q1 over R1 plus, it depends on whether or not the next thing is negative or not, by the way, but K Q2 over R2 plus K Q3 over R3 plus K Q4 over R4. And here's the thing. Distance can't be negative, right? All you have to do is combine these like you would adding any other numbers or subtracting. So for example, I'm going to pull the K out. Do you mind? I don't have to write it a million times. Q1 was 10, right? So it'll be 10 over R1, whatever that is, minus 7 over R2. Why the minus? Because it's a negative charge. It's that easy. Plus 5 over R3 minus 1 over whatever R4 is. And of course, if we knew the distances, I would know those numbers and blah, blah, blah. But the point is, there's no vectors. Just add and subtract. That's for a collection of point charges like we see there. All right.